welcome. So we just got time to make a start on this. There's a next chapter. So we're going to talk about current and resistance, and frankly, some of this I'm really interested in, and some of this I'm not so interested in. So I'll try and be very clear about this. When we have an electric field, across a wire, then it causes charges to flow. Why do charges flow? Because the wire is made out of metal, and metal has loosely bound outer electrons. There's covalent bonding where everything's pretty well locked up. There's ionic bonding where pretty well everything's locked up. And then there's metallic bonding where it's kind of like it's very loosely bound. So if you're an outer electron in a metal, you don't even know which atom you belong to. You're kind of floating around above them all. And that means any electric field is able to kind of move you to one side. So we can define this thing called the current. We know that charge flows by electrons rather than positives, but before they knew that, they picked the positive flow as being the current direction, and there's no point in changing it, so we just live with it. It's like you get used to it. Current is, as far as we're concerned, the flow of positive charge carriers. We just live with it. It's fine. And an electron going in one direction is like a positive charge carrier flowing in the other direction. So we can define this thing, and that's what the three lines mean. We can define this thing, which is the current. That's what the three lines mean. Definition. So my average current equals my flow of charge over my flow of time, if you like, delta Q by delta T. Instantaneously, it's that. How much charge do you get flowing down your wire in a given time? We can say current is the rate at which charge flows through a surface or an area. Current is measured in amps or amperes after ampere, and it's 1 coulomb per second. And the direction of current flow is taken between the flow of positive charge. It goes from the positive terminal of a battery to the negative terminal of a battery through an external circuit. Now we do a bit of math, and we're trying to get home a point on this. And this math is basically telling you that although the charge carriers fly, they are going so fast, the current is not fast moving. So, what's going on there? So here, imagine a couple of charge carriers, and they're going through a piece of wire. I'm going to think of the piece of wire like a piece of pipe. And it's got an area, so we have this area at the end. And it's got a certain length, so we'll call that delta x. And basically, I start asking myself some fundamental things. I say, let there be little n charge carriers. Let there be little n charge carriers per unit volume. Well, copper will have more charge carriers per unit volume than aluminum. And again, you can look in the engineer's handbook and you can look up how many charge carriers there are. So the more free charge carriers there are, that's not every electron. It's the ones that are free to move. Not all electrons are charge carriers. So we can look those up. We can look at the materials and see which are better. Let delta Q be the charge in the section being considered. So this contains a section of charge delta Q, an amount of charge delta Q. And we say, well, okay, how do these things relate? And we say, well, the amount of charge in my little section of wire is equal to the number of charge carriers per unit volume times the volume times the charge on a charge carrier. That just makes sense. And then we say, well, that's interesting. I can imagine an average average velocity of my charge carriers. And I'm going to call that my drift velocity. And I can represent this distance by saying it's velocity multiplied by time. That makes sense. Yeah, remember from your kinematics, distance traveled equals velocity multiplied by time. Velocity multiplied by time. So rather than this volume, Rather than this delta x, I can say the volume is the area multiplied, not by delta x, but by this drift velocity multiplied by time. And that's interesting. Okay. I don't know what the time is, but here's the nice thing. My current equals the amount of charge per unit time. So if I divide this expression for the amount of charge by unit time, I get my current. So my current is equal to the number of charge carriers per unit volume times the charge on a charge carrier times the drift velocity times the area. And that makes sense. If you want to know your drift velocity, just rearrange it. Your drift velocity equals the current over the number of charge carriers per unit area, unit volume, times the charge on a charge carrier divided by the area. Why is there a difference between my drift velocity and my electron's speed? Because electrons basically travel really fast until they hit something. That's one thing. And so for an electron, I have to take into account it's hitting things all the time. So it's making a kind of weird progress. If there's no electric field, it hits something and bounces back, and 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 hits something and bounces back. It never goes anywhere. So it's got a high speed but zero velocity. But if I put an electric field here, then what happens is it hits something and bounces, but hits something and bounces, and hits something and bounces, and hits something and bounces, hits something and bounces, and hits something and bounces. And there's an overarching drift to it. And if you ever went to the fair, the fair was just here. Man, you know, I used to, as a kid, I'd take all my little spending money to the fair. I'd lose it in about 10 minutes. My older brother would just ridicule me. I'd feel so upset. But I'd never learned. The next year I'd go back. And then as I got older, I realized that all these games are designed to take my money away from me. And this is the classic. You get a piece of wood and you put a whole bunch of nails in it. And then you have this little ramp. And you say to this little 7-year-old, put your money into this slot and we'll see if you win. The definition of winning is getting your own money back. I don't think that's winning, okay? And what they do is they say, okay, we'll have a whole bunch of pots down here, and here you go, Tony. If your money goes into that pot, we'll give you it back. But if you go into these other pots, better luck next time, okay? So the coin comes in, and it hits, and it hits, and it hits, and it hits, and I'm getting really excited, and then it hits, and I'm in tears, right, you know? And the guy might as well have come up to me and said, give me your money. And I just said, that's not a very good game. That's called holding me up. But it has the same effect. All they do is they have this little game inside, and my emotions go, I'm going to win. I'm going to win. I'm going to win. I'm going to win. And then you lose, okay? What you should really do, I suppose, if you want to hold people up, is say, think of a number between 1 and 10. If you think the right number, you win. You can keep your wallet. If you don't, better luck next time. I think you'd still get arrested. So it seems to me these guys should get arrested. Anyway, so what's going on? What makes it so interesting is the delay, isn't it? It's the fact that you hit and you bounce and you bounce and you bounce. So you get this excitement of, am I going to win? Am I going to lose? But you are going downwards all the time. Your speed is really quite big, but your velocity is relatively small. Your velocity is in that direction because you're going downwards, but you go slowly. And that's what's happening. Your speed's high, but because of all these interruptions and because of this tendency, it's just the drift, it's like a projectile bouncing around, then your velocity is quite slow. Okay? So high speed but low velocity. Okay. we can define this thing called the current density, which is the current divided by the area, and I can work out a terminology for that, and frankly, I don't care that much about it. Know it's there, know you can work it out, know that the current density is the current divided by the area, but I don't particularly care about you knowing that it's the number of charge carriers. You can figure that out, yeah? You can figure that out. So, you could plot a graph of current density versus the electric field that's causing this current, and you get something that looks like this, where you plot the current density on the vertical axis and you plot the electric field on the horizontal axis, and you get these straight line graphs. If you increase the electric field, you increase the current density. More current flowing cross-sectional area. Yeah? And we can talk about this in terms of conductivity. And we say if we get a lot of current crossing unit area for a small electric field, it's a high conductivity material. And if we get a low current crossing unit area for a high electric field, it's a low conductivity. And okay, I can get that. But what I really want to get to before the end of class is this next one, which is that if rather than looking at current density, I look at electric current, and if instead of electric field, I look at potential, I get a graph which is similarly linear. And this is an ohmic relationship. And that gives me that equation. Delta V equals IR. And only one wrinkle. People will often tell you that the slope of this graph is resistance. And it's not. We plot it this way because current is the dependent variable and potential is the independent variable. We set the voltage, we get a current. But this expression has Y being delta V and I being on the X. So in reality, this is 1 over the resistance, and this is, the slope is 1 over the resistance, yeah? So the slope is 1 over the resistance for this graph. Ohm's law. So my dad was in the Air Force and he got took into navigation school. He failed the pilot's exam, so it was either navigation school or he was a gunner. Life expectancy for gunners was 6 hours in the air. Navigation school was 18 months. He passed. He was very lucky. He passed. He got 18 months. It taught him, basically it was college for him. He'd have never gone to college. It was college for him. They had all these guys and they had to train them. And they didn't have the luxury of saying, are you good enough to be in this class? It's like, you know, hey, you're going to be a navigator. So they had to find ways of teaching people. Navigators were responsible for doing all the vector stuff. They're responsible for also communications in many cases. They had to be able to work the wireless system. If the plane crashed, they had to be able to repair the wireless. They were like, you know. So a lot of training, 18 months training. And when I was a kid in high school, I was learning about electricity. He loved amateur radio from his RAF days. He loved amateur radio. It gave him enough to get him going. So I was talking about Ohm's law, and my dad was reading the newspaper, and he goes, "Which one?" And I said, "Ohm's law." And he says, "Which one?" I said, "The physics one." He goes, "No, there's 3 Ohm's laws." And I said, "What are you talking about, Dad?" And this is like he's like 45 by this stage. He goes, delta V equals IR. He goes, I equals delta V over R. He goes, R equals delta V over I. He says, I think you better do some studying before the next test. And I said, I think I have algebra, you know? And at first I thought it was the craziest thing out. And then I thought, think about it. You got all these people and you're trying to train them so they can do the job. And you don't have time to teach them algebra. You just got to make sure they know how to do it. So tell them there's 3 equations. They can apply the equation they need to do, and it works. So it's really quite remarkable. I really care about this. We'll draw a line there. I really care about that. Next time, I'll get rid of this. Next time there's a quiz. Oh, no, not next time.